And the latest theme that will be launched quite soon, or is in the process of building up, is called CleanTech. And to talk about this, I figured I'm going to dive into the scientific literature and look up what CleanTech actually means. And the first dive into highly scientific resources was, of course, a Wikipedia search. And Wikipedia actually says this very concisely. CleanTech could be processes or products or services. These are three very different things, right? That reduce or aim at reducing the negative environmental impact of the process or the product or the service, either, for example, through improving energy efficiency, reducing or the use of resources, or increasing environmental protection. So you realize already there's an incredibly broad range of things that could be counted under clean tech, right? These could be technologies that are related to recycling or to renewable energy, or even to information technology, green transportation, electric motors. Wikipedia lists a whole lot more. And because of this high diversity of themes possible under CleanTech, we decided to go about this theme a little bit differently from the other grand themes. So rather than having one big overarching theme, we decided to give the opportunity to 3 individual research groups to contribute to this topic. However, we did focus it a little bit. We gave that theme a focus on climate change, right? And when you talk about climate change, you talk about greenhouse gases, you talk about carbon footprint, and so we gave it that angle. That said, there will be several presentations that are going to be really short, 3 to 4 minutes, and we invite all 3 themes to present what they intend to do. We also hope that even though that we identified 3 groups, that they will actually form a community of researchers that work on clean tech. Because I think even with the given diversity of research projects, it's great to talk to each other and learn from each other, and to see how everyone contributes from their own angle to this bigger cause, so to say, to make technology, to make processes less environmental unfriendly, more environmental friendly, by either reducing pollution, by reducing the release of greenhouse gases, etc. And so we will hear from 3 groups. I'm going to name all 3 of them, and then I'm going to call upon the first person to present. The first group is spearheaded by Salman Craig, and it focuses on buildings as a global carbon sink. So buildings, we're talking building, houses, high-rises, whatever, and using these as a sink for carbon. The second group is spearheaded by CJ Lee, and their title is Engineering Nanocatalysts for Solar CO2 Conversion to Chemical Fuels, so capturing CO2 to convert it to something that is useful as a fuel. And the third theme is spearheaded by Jeff Bergthorson and entitled Zero Carbon Metal Fuel Energy Technologies for Climate Action and Poverty Reduction. And you can see with that third one already, we're getting that humanities sides into the projects that we really would like to encourage more and more, to, rather than focusing exclusively on the research and scientific and engineering side of things, to actually include what it means for populations, what it means for our society. I'd be delighted to introduce the first speaker, Salman Craig. I hope he's online to give his, I think you were given 3 or 4 minutes to present your theme, and please go ahead.
Thank you, Anya. Thank you, Heather. I'll just start. So buildings as a global carbon sink. Here's our team. So briefly, we have Benoit Cote, who many of you know from Natural Resource Sciences, director of the Morgan Arboretum, and in summary, he knows how to manage forests. We have Michael Gemtrude and Kiel Mo, both from the School of Architecture, and in summary, they know how to design and build with wood. And me, the PI, Salman Craig, also from the School of Architecture, and I guess I know how wood buildings can do thermodynamic work, or at least have some ideas for how to do that. So the challenge, or the big numbers that we're attempting to tackle, human activities are currently responsible, as you know, for about 40 gigatons of CO2 equivalent per year. Of that yearly rate, approximately 30%, or about 16 gigatons, is because of energy use in buildings. These emissions will fall if nations retrofit old buildings and shift to renewable energy. But we're a bit more concerned about the impact of new construction. The production of new building materials, mainly cement, steel, and glass, is responsible for about 4 gigatons, or approximately 10% of global emissions. And as the world's population grows in the coming decades, driving demand for new construction, these so-called embodied emissions are likely to dominate. While it's straightforward to make buildings more efficient over their lifetime, the carbon emitted to produce them is irredeemable. So we are interested in the following question. Is it possible to transform this potential threat to the global climate system into a powerful means to mitigate climate change? One possible approach is to increase the share of timber in new construction worldwide. The latest scientific estimates suggest that long-life timber products have the potential to store the equivalent of 0.5 gigaton of CO2 in new building stocks per year. This rate puts wood buildings on par with other frontrunners for carbon storage in the technosphere. And this is where we intend to contribute. As well as giving structure to buildings, we think timber buildings can harness ambient energy to control their interior climate. We aim to upgrade timber to multiply its drawdown potential, so that 1 unit of stored carbon can negate several units of emitted carbon. Our starting point will be a carbon inventory of the Morgan Arboretum. What impact do harvesting practices have on the carbon sequestered by soils, or the likelihood of forest fires? What would the carbon sequestration be if we just left forests alone? A carbon inventory of the Arboretum, supported by ongoing measurements, will help us to understand the risks and dynamics of carbon drawdown in managed forests. Then we can extend our models and examine scenarios for carbon storage in new buildings. Not at the scale of individual buildings, at what it's currently limited to, but at the scale of regions in coordination with Canada's managed forests. If the Arboretum provides our ground truth, then our most pioneering work, we hope, will come from a profound reinterpretation of building systems. Building assemblies are ripe for radical integration. The organization of building assemblies into different subsystems reflects the organization of labor and knowledge in the industry. When the schematic design settles, the different teams need to be able to work independently on their allocated parts. This way of working helps ensure projects get done, but it is unsustainable. This fragmented approach has produced a surfeit of over-specialized materials from a globalized supply chain, flooding the market to fill niches that need not exist. Suppose instead we design timber elements that give structure to the building, but also provide low-grade heating, cooling, and ventilation, not by adding dissimilar materials, but by shaping wood to optimize exchanges between heat and air. Then we can radically simplify those assemblies, negating emissions from cladding, insulation ducts, air conditioning, and all the hidden materials you never think about. So here is one of 2 CleanTech projects we aim to develop using MSSI funds. Since 2017, we have been pioneering the engineering of building envelopes that work as heat exchangers, not as insulators, starting from a structural material and optimizing air channels in them. One significant finding is that wood, because of its low thermal conductivity compared to other structural materials, is the only standard building material able to exchange heat to incoming air at a feasible rate. That is an exchange rate that can meet U-value standards without leading to overventilation. And by upgrading ventilation in this way, timber in this way, we hope to radically simplify building assemblies and obviate the life cycle emissions from other materials and standard HVAC systems. So to summarize, we propose to examine the potential of innovative timber systems to provide long-term storage of atmospheric carbon in synchrony with managed forests. And our long-term goal is to develop integrated biomaterials and value-added supply chains that can obviate up to in the order of 0.5 gigaton of CO2 per annum of construction-related emissions. Thank you.
Thank you, Anya, and thank you, Heather, and the whole team at MSSI for preparations for this, and of course also for helping us to realize this project. So if I can comment a little bit about bring the idea here, I want to focus really on the big picture idea and not actually how we're going to deal with the details here, but that's the focus for today. How do I change it here? Okay, so just like what Professor Lee was saying, what we're really looking for as we go forward in the society is some way of storing and transporting clean electricity for a whole host of different applications. That can be heavy-duty transportation, off-grid power generation, and it can even be for international energy trade. How do we take excess clean energy from some countries that can produce more than they need and ship that to other countries that don't have enough? And we want to try to find a way to do that without any emissions. And it's difficult to transport and store electricity, as we can see from where batteries sit on this energy density diagram. Batteries, while improving, have a very low amount of energy per mass or per volume compared to our traditional fossil fuels that we're used to. And so our group has been working for the last 10 years or so on maybe a radical concept, which is to use metals as a recyclable fuel. And so the idea is that you can take metals in powder form and burn them, as I show here on the top right, to produce heat, and those are flames of iron powder and aluminum powder burning in air. Or we can react some of these metals, things like aluminum, with water and generate hydrogen on demand. And so those two ideas then enable us to think about actually using metals as a way of transporting and moving energy around with a potential to harness that energy. And so our focus is on the whole cycle, but to just bring a little bit more focus to the technology side, because metal production is a relatively more mature topic, we're looking at two technologies. One is what we call the dry cycle, where we directly burn metal fuels with air, producing heat, and then generate that electricity from that heat using heat engines. So that's things like steam engines and Stirling engines, etc. Or react that metal fuel with water, generate hydrogen on demand, and then fuel things like gas turbine engines, reciprocating engines, fuel cells, and all of those equipment that we have. In the latter, it's basically enabling the hydrogen economy without having to transport and store hydrogen directly. And so the vision that we have for this whole concept is really taking clean renewable energy on the one side, storing it into a form that's portable, that's safe, that's shelf stable. You can leave it outside in a heap for some years, at least in the case of something like aluminum, and it won't degrade and rust on its own. And then use that when and where we need it to generate electricity, mobility, and heat for high temperature applications. And then the product is a metal oxide. In the case of iron, the product is rust. In the case of aluminum, it's aluminum oxide. And then we would take those oxides and return them and recycle them. So this is a circular economy where energy gets moved from place to place, but there's no actual emission of matter and pollutants into the environment. And that's the goal, to find it. And so within the project, we'll not only focus on the production of power from those, where there's technologies, and we're looking at ways to do that. We'll also look at the recycling and how we can do that recycling in a carbon-free way. And then as well, what's the bigger picture of how can we use this type of a concept to alleviate poverty? So I'm just going to introduce quickly the project team that's here. Mathieu Brochu and Fiona Zhao are working on additive manufacturing and design for that, and how we can use that as a technique to improve our technology. Sylvain and Mathieu are working on technologies to reduce. Professor Coulombe and Mathieu Brochu are working on technologies to do the recycling side. Professor Frost and I have been working for many years on the technologies of both direct combustion and metal water reactions. And then we have Professor Etienne Jor working on the economics and how do we use this concept to tell a story that is, how can a resource-rich country like Canada actually see itself transitioning to a low-carbon economy in a way that will bring prosperity to all regions. And Mathieu Chemin will take that one step further and look at how can such a technology bring prosperity and improve quality of life for people that are currently in developing countries as well. And we see that this is a way of enabling that in that context. So I'll just leave with a video of an iron flame so that you can see it burning live, and the picture of the sparklers so you can call that to your mind.
The next project is spearheaded by Hong Guo, who's not available to present today, I believe, but CJ Lee is presenting for him, so please go ahead.
Okay, thanks, Anya. Our project is to engineer nanocatalysts for solar CO2 conversion to chemicals and fuels. So the team involved Professor Han Ge from the physics, and his expertise in multi-scale modeling, material physics, device physics, and myself from the chemistry. So the main problem is the modern society relying on the petroleum as a fuel and also chemical feedstock. It's a one-way direction to turn petroleum into carbon dioxide as final product. How to turn them back from the carbon dioxide into the fuels and chemicals will be a major sustainability issue in future. Nature actually, in fact, using solar energy and enzyme as catalyst to turn carbon dioxide and water into organic molecules. And inspired by nature, what we would like to do is to design photocatalysts, just like enzyme, again, use solar energy to turn carbon dioxide and water into chemicals and fuels. Of course, together with other people working in the field, ideally in future, we'd like to really alleviate the CO2 issues in the atmosphere, and also to use the CO2, in fact, as a future chemical and fuel feedstock. Thank you.